This is lesson 1, the overview lesson of the wireless communication portions of this course. We're in part 3 of our second module, which is TT&C technologies. And you can see as we walk through the wireless communication portion of the course, a few of the other topics we're going to be discussing are the modulation process, the use of antenna, and then something called the link equation that we use to perform design trade-offs regarding the wireless communication link in the design phase, and then to perform analysis and project performance about the link, the communication link during the operations phase. We use wireless communications in order to get information from one location to another. In order to do that, we go through a transmission process to convert our bit stream, our string of ones and zeros, into a wireless communication signal, a radio signal in this case. And then we go through a receive process to convert the electromagnetic wave, the radio wave, back to ultimately the original string of bits. As we do that, in transmission and receive, there are several steps we go through. And in addition, once the signal exists as a wireless radio signal, it's going to travel between the two antennae. It can travel with or without the use of a medium, so it can travel through the air, but it can also travel through a hard vacuum. The hard vacuum is space in this case. And as it does that, it's going to suffer a little bit. It'll be attenuated, distorted, noise will be injected, it'll be perturbed in a number of different ways that will make receiving a challenge for us, and that's one of the topics that we certainly will address in this portion of the course. In terms of some vocabulary, some definitions of various functions that we're going to be talking about, this slide attempts to summarize those. So we can start off with what we call the modulation process. Modulation is the process of taking a high-frequency wave and changing some characteristic or parameter of that wave in order to convey information. And so a really simple example you can see off there to the right, if we have an information signal, which in this case is the upper long wavelength or very low frequency signal, we can take a higher frequency signal and we can change the amplitude of that higher frequency signal in order to convey the original information. And this is called amplitude modulation. You can see an example of it there to the right. Now, once we modulate it, we've converted the form of our information from our baseband signal, which is really the original information signal, into this modulated carrier wave. And we have to go through a process to retrieve the information. That process is called demodulation, and that's the process by which we extract the original data by looking at the changes to the standard signal we used to begin with. Another thing we're going to be doing is filtering. We're going to do that in order to get rid of unwanted frequencies. Some of those frequencies are going to be injected in the communication path itself. It would be noise from other sources of radio emissions, but we also will be filtering out signals that we create through the engineering of the communications equipment and system itself. And those frequencies are a natural byproduct of the process through which we go to modulate our waves, but we just don't need them ultimately for the receive process. So we're going to be removing unwanted frequencies, some of which come from outside sources, and some of which actually come from us. We're also going to be amplifying things as we broadcast waves. They're going to get less and less powerful. They'll get weaker, smaller in amplitude, and a large amplitude wave makes it easier for us to process. And so in several steps, we're going to be taking the waves we have and amplifying them in order to make them easier for us to work with. The transmission process is actually the process converting the wave from a voltage in a wire to an electromagnetic wave, a radio wave traveling through space, and then reception is converting those electromagnetic waves back to the voltages in a wire. And that comes about through the use of an antenna. You can see the graphic to the right. We see the green portion, which represents a wave, and as it travels from right to left, that wave will induce a voltage in our antenna, and that voltage will be placed across a resistor and will result in electron motion in the form of current, and we can build a circuit around that in order to receive, and then we can reverse the process in order to transmit. We can force current through the antenna. It will induce a voltage, and that will generate a wave. That's how we transmit information ultimately. And another thing we're not going to speak too much about, but just to put it in there, oftentimes we're converting frequencies from one level to another, and we may do this in one or more steps in order to aid the processing and the various the use of different components that we have at our disposal. So we're going to use radio waves in the microwave range of the electromagnetic spectrum in order to wirelessly communicate information from one location to another. And these are, again, electromagnetic waves, and electromagnetic waves have an electric field component and a magnetic field component, and they are perpendicular to each other, as you can see in the graphic at the bottom of the slide. These waves basically travel at the speed of light, and again, they can travel both through a medium as well as without a medium, like through the vacuum of space. In general, in terms of just a little familiarity with waves, you can see the electromagnetic spectrum there, and you can see in particular sort of the sweet spot for satellite communications, which is up in the microwave and radio range, well out of the lower frequencies, the higher frequencies, which is where visible light is, ultraviolet, X-ray, gamma rays, those sorts of things. So we're at, relatively speaking, fairly long wavelengths, low frequencies, large wavelengths. The reason we use microwave electromagnetic radiation for satellite communications in particular is sort of implied by this chart here. And this is a chart that shows how much energy in a wireless wave is absorbed when you try to send it through the atmosphere. So you can see at the very the left-hand portions of this particular plot, and the extreme right-hand portions, and then it's sort of a sweet spot in the middle, we're getting almost 100% absorption of the waves in the atmosphere, which basically means if you try to transmit at that frequency through the atmosphere, almost all of the energy in the wave will be lost. And it gets lost by exciting the various particles in the atmosphere, which results in a lower power that is received on the other side of the atmosphere or through the atmosphere. So when we see the radio region, and in fact even the visible light region, one reason why we can see the sun is, well, first of all, it's very powerful, but there's a nice window in the visible range for energy to pass through the atmosphere. And the same is true with microwave range, and that's the range that we use for satellite communications. You can see almost zero absorption at those frequencies, those wavelengths, and you can see the graphic. There's a nice large dish pointing up to the sky, and it's another window for us to pass energy through the atmosphere from a satellite to a ground communication station and back. In terms of a few characteristics of radio waves, we're going to go through several slides, each talking about a different characteristics that we're going to refer to many times. The first one of which is frequency. Frequency is the number of oscillations per second of the wave. Typically, we transmit and receive at different frequencies, and we realize that the frequency of the wave versus the frequency range of the receiver that we're using, the receiver will have, if we tune the receiver to a specific number, receive a wave of that specific frequency, the receiver actually has a window there, sort of a bandwidth, a range over which it can receive. And we want to make sure that we are tuned in to at least match this window, this bandwidth window, um, over the frequency that we were really trying to receive. Otherwise, the receiver is going to filter out everything else, or at least it was going to try to filter out everything else. So we refer to these as channels in many cases, but our ability to tune into specific radio frequencies is built into our receiver. And we discuss this in terms of the use of various frequencies. The choice of frequency itself will affect performance in terms of how much information we can get. We can modulate under the wave, how much absorption there'll be through the atmosphere, as we saw in the previous slide, the choice of antenna that we have, and therefore the size and mass of that antenna's performance. These are all frequency-dependent kinds of things. And then another conversation we often have with frequency is sometimes we see a shift in the frequency. This is a parent shift, so a satellite, as it travels across the sky, it's broadcasting at a specific frequency, but the frequency we will see or we will receive from the satellite will be affected by the Doppler shift, which is a relative shift in frequencies caused by the relative motion of the transmitter and the receiver. And for low Earth orbit spacecraft, this could be on the order of 10 kilohertz or so. And the waves we're using, the frequencies we're using, are sort of in the hundreds of megahertz. So it's a small fraction, but enough to affect the ability of the receiver to receive it if you don't correct for it in many cases. Down at the bottom of the slide, you can see the lingo, so to speak, of various bands. We talk about typically the use of VHF and UHF bands for the ham radio transmissions that we use to control spacecraft or to monitor them. And sometimes we talk about S-band radios. We have an S-band radio on the small NASA spacecraft that we control. So you can see that's really sort of within the UHF and SHF bands. So there's a mixing and matching of terminology, and that chart there at the bottom of the slide to the left attempts to break out these regimes for you. And we will be talking a lot about VHF, UHF, and S-band communications. Another radio characteristic is power. You can imagine sort of a very idealized, what we call isotropic transmitter. And if we are broadcasting a signal at a certain power level, the transmit antenna is broadcasting that amount of power, and as the signal propagates through the air, you can imagine going in all directions, sort of an omnidirectional sort of model of where the wave is going. It will look like a sphere that's growing in radius. And that wave front, which is really sort of represented by the surface of the sphere, has all of the energy spread out over it. And so as the distance increases, as the wave front propagates through space, the energy sort of gets spread over more and more surface area. And as a result, if we are standing a certain distance away with an antenna of a certain size, the farther away we are, the less power that will be received by the antenna, because we are intersecting a smaller and smaller fraction of the total surface area of the sphere as it gets bigger and bigger. So this falls off as an inverse square law. So if we double our distance between the receiver and the transmitter, we're going to suffer a loss of 1/4 of our power. Another characteristic is the polarity of the electromagnetic wave. You can see a couple different diagrams there at the bottom of the slide. I'm showing just the electric field for simplicity, because the diagrams get pretty busy if I try to show the magnetic field as well. But if you remember from a previous diagram, the electric field and the magnetic field are 90 degrees apart. So the orientation of the fields is the polarity, and it makes a difference in terms of that relative angle when we transmit and receive these electromagnetic waves. And so you can see some linear polarization vertically and horizontally on the left in the blue. And you can see examples of circular polarization where we have sort of a continuously rotating wave as it travels through space. And again, the magnetic field is 90 degrees out of phase with the field that's shown there, and the one that's shown is the electric field. If we have a vertical monopole antenna, which we'll talk about, we're going to generate a linearly polarized wave, and it will be vertically polarized. If we take that same antenna and we hold it horizontally, we will have a horizontally polarized wave. If we take that antenna and it's on a spacecraft that's slowly tumbling, then it's going to generate circular polarization, either to the left or to the right, depending upon the way the satellite tumbles. And so this is the way the E field propagates through space. And ultimately, when we're trying to receive this wave at the other end, we want to align our antenna accordingly. If the wave is coming in with vertical polarization, we want to hold our monopole antenna straight up. If we were to hold it horizontally, we're going to suffer a loss. Likewise, if it's horizontally polarized, we'll want to hold the antenna horizontally, but if we hold it vertically, we'll suffer a loss. If we don't have the right handedness of circular polarization, then we will suffer a loss from that. Or also, if it's one or the other, if it's linearly polarized and we assume it's circularly polarized, we will suffer a periodic loss as the wave rotates geometrically in space. So the orientation of the wave, this characteristic of polarity, is important to us just as much as the frequency and the power. Now, as waves propagate through space, they can get from one location to another in a number of different modes. Things are known as propagation modes. And there are four of them that people typically talk about. The one that we're most interested in for standard communications is a direct line of sight, straight line traveling between the transmit antenna and the receive antenna. There are other ways for the waves to get from one location to another. Ground waves are examples of the waves sort of hugging the ground even as it curves away due to the curvature of the Earth. There are sky waves that bounce off of different layers of the atmosphere, and so on and so forth. Those are all sort of secondary modes of propagation as far as we're concerned, and they really would show up as noise to us. We would not, for standard satellite operations, we would not count on them in terms of engineering the communication system. Now, that said, there are lots of ways for us to receive disturbances and interference due to the way that waves travel. And we're interested in the direct line from the transmit to our receive antenna. But as the satellite broadcasts, the waves do all sorts of things. They go in different directions. They can bounce off of large objects and reflect. Because they bounce off of large objects and sometimes don't go through them, you can get shadowing effects. They can have a diffraction turning effect around sharp objects like mountaintops. They can reach your antenna because of all these phenomena through multiple paths. And you can see in the lower right-hand corner there, we have a direct path from the antenna to our, in this case, car. But we also have paths that reflect off buildings or off the ground. And that results in receiving the signal multiple times. We get the first strong signal due to direct propagation, but we get a slightly delayed and weaker signal from what we call multipath effects, these other reflections and other ways for the wave to reach you, and that looks like noise to the communication system, and we want to be able to filter that out, ideally. We oftentimes have to share communication channels. The channel is really that frequency range we spoke about before. You can imagine your radio, you tune in to a certain station. That station really is a certain frequency, plus or minus a little bit. Um, and there's only so much spectrum, which means there's that frequency range can only be chopped up into so many different parts, um, especially when you need sort of a wide channel because of the how much information you're trying to broadcast at a certain frequency. You can see the plot in the lower right hand corner, and you're not supposed to decipher that in any way, but really that's showing you radio allocation, channel allocation at different frequencies. You can see just the enormous number of assignments on how uh, the spectrum itself, the different chunks of frequency ranges, are assigned for different purposes. And this is something that is heavily regulated um, and coordinated between countries and agencies and everything else. And in general, you need a license in order to transmit at any significant power level in terms of you being a user in this community that shares the radio spectrum. And I'll point out that we are licensed operators. We're a licensed radio station in order to communicate with the spacecraft that we control. And we'll talk about that a little later, but these NASA spacecraft that we deal with typically have two radio channels. There's one at S-band, which uses really an unlicensed commercial networking sort of card, but we use it in a way that violates its license because we are magnifying it or have such an intense gain with our antenna, our directional antenna. We exceed the equivalent power level coming out of the antenna along its bore site. And for that reason, when I say we violate it, we violate the criteria that makes it an unlicensed radio. So we go through a process to license all of our parabolic antenna. And we have a license at every location in order to do that, in order to broadcast. We also have ham radio licenses that allow us to use the amateur radio spectrum. So even for amateur use, you go through a process, and that's actually a personal process. Individuals will receive the ham radio license in order to use those frequencies. When we talk about really trying to get efficient use out of the spectrum, there are a couple different ways that we can negotiate sharing. And to really go through these, because you're going to hear some of this terminology, the first way is doing it by space, which means um, if we are both trying to use the same communication channel, if we're far enough away from each other, then by the time my signal gets to you and your signal gets to me, the power levels are so low that it makes no difference. And so this might be reusing channels in various parts of the country or around the world. That's a very simple thing to do. And as long as you maintain your distance, you don't have to coordinate or anything along those lines in terms of the real-time use of the channel. So this is taking account of the local effects of propagation of radio waves. Another way of doing it is to divide up by frequency, which I've already sort of suggested we do. The official term for this is frequency division multiple access, which means we divide by frequency and therefore we allow multiple users to access the radio spectrum at once. And what we all agree to do is we agree to operate at within a certain frequency band. Typically, we're assigned a certain center frequency with some plus or minus bandwidth, and this is called the channel. And each of our channels is separated by a little bit of buffer called the guard band, and that allows each of us to simultaneously use the radio spectrum, but we're all doing it at different frequencies, and we're using equipment that when we transmit tries to limit our broadcast to that frequency, and when we receive tries to filter out anything outside of our particular channel. And that way we can all use the spectrum at the same time. Another way of doing it is to use the same spectrum but to split it up by time, and that's time division multiple access. This could be at a very long interval, like a particular radio or TV channel might schedule different shows, and so in that sense, kind of each user, each show is using the same channel, the same spectrum, but at different times. And through the schedule, you figure out who gets to broadcast at what time, or you can do it very quickly. You might do it at the many times a second, and you need to have equipment that allows all the users of the channel who are attempting to use it simultaneously know what fraction of a second they get to transmit on. And so you can have a sort of a fast switching mode of time division multiple access. Almost always, time division multiple access is combined with frequency division multiple access. And so you're doing this on a channel by channel basis as opposed to just using all of the radio spectrum at once, but at different times. Then we have a fourth approach, which is sort of a modern communication approach called code division multiple access. This is an interesting beast. This potentially lets you multiple users use wide swaths of the frequency, and potentially the full spectrum. That's very typical, but much larger ranges of frequency than a typical channel, and they all do it at the same time. And the way they do this is they have a very clever way of coding the information in their broadcast. So these all interfere with each other, but the coding technique allows you to tease out the broadcast that you want to hear on the other end. And so in that sense, you use it, you share the spectrum. But really, what you're doing is you're interfering at the same time, but you're just being clever enough in order to be able to withstand that interference. And for those who use code division multiple access, um, you might even be using the frequencies that a standard television or radio station may be using, but you are at such a low power level that you look like noise to them as well. So this is kind of an interesting thing, and this is a level of detail that you don't need to worry too much about in terms of quizzes or tests. But here's a very simple version of a coding process for CDMA multiple access. The idea is I have two different users down on the bottom left, um, both encoding their messages using a CDMA technique. And user A, which is on top, has a message of 1, and user B on the bottom has the message of 0. But they both also have codes. They have a bit sequence, which is sort of their code. You can almost consider it to be a password if you want, although it's very likely that this is a publicly accessible password, but it's a code associated with the user. Uh, Now, what happens is you can see the explanation there in the set of bullets, and I'll let you walk through this, and we'll go through this in the in-class portion as an example for those who are interested. You go through a process to combine the message with the code, and out the other end comes the encoded message. Um, and that's what gets broadcast in space. We use that to modulate our waves. And those superimpose in space once they're out because they are, in that sense, interfering with each other. And each receiver receives the superimposed version. And given that as an input along with the code of the message they're trying to receive, you go through a process to decode the message in order to extract the original bit. So, a very interesting approach. It's not based on an isolation in the sense of frequency or time, where one user gets a certain chunk of spectrum for a certain amount of time. This allows everybody to use it at the same time, but it requires a more cumbersome encoding data processing technique in order to make it happen. This is, in general, kind of the way cell phones work. Another thing that we do with communication systems is something called frequency hopping. And this is an agreed upon shift in frequency between the transmitter and the receiver, either a priori or um, oftentimes even the receiver knows um, the range of frequencies or channels that it will use, but when to switch is synchronized by the transmitter or a master unit in the communication link, a master transceiver in that sense. which will say now it's time to switch to the next frequency and go to the next one in your pattern. And you can see in the diagram the top versus the bottom. You can have slow versus fast hopping, and really the use of slow versus fast is the length of the bit. How does that compare to the length of the window that you're at any one frequency? And so you can imagine hopping frequencies several times per bit, or you can imagine hopping frequencies less than that, and several bits come in at each frequency level. So in the example here, you can see at the very top the user data is a string of bits 0, 1, 0, 1, 1. And then the second plot down is a slow hopping strategy where you're centered for the first time window down around frequency 2. And it looks like there's a little bit of frequency shift keying there above and below frequency 2, depending upon if the bit is a 0 or 1. But then after 3 bits, you shift to another center frequency, and you are doing frequency shift keying based on that new center frequency. And then similarly down at the bottom, this is a fast hopping example, and you can see that for each bit, and in fact for the 0 bit, the very first bit on the left, in that case, this particular system is shifting 3 times during the length of the first bit, and that bit is 0, and you can see a frequency shift key below the center frequency for each one of those, indicating the 0 value. So the notion is to switch frequencies. You can do it fast or slow with respect to the bit rate, and this needs to be synchronized to everybody else that might be listening to you. It's very hard if you don't know the frequency pattern to know where the information is going in terms of how it's being modulated at different frequencies, so it may be hard to track. And it looks like noise. You're usually doing a frequency hopping system at low power levels, and so you can use, again, kind of large swaths of spectrum in order to achieve this. Many times frequency hopping is actually combined with CDMA. It doesn't have to be. But it may look like noise to other users, and it's hard to know where to listen in order to track the hopping pattern over time. In that sense, sometimes people think of it as a form of security, and it certainly is. It would not be a form of encryption, though, because encryption is the algorithm that transforms the data as opposed to a technique that modulates the data, even if that modulation is on a changing frequency pattern. But you would be relying on an obscurity model in order to just not allow someone to know what the next frequency is, as opposed to true security, which is publicly declaring everything and still making it hard for them to figure out what's going on. So, in summary, we use microwave frequency range radio waves in order to get information back and forth wirelessly between spacecraft and the ground. One of the main reasons we do that is because we have a nice window of low absorption through the atmosphere during at these ranges. If we just were to sort of generate an electromagnetic wave at the frequencies of our baseband data, almost always that's very slow, relatively speaking, and it would all, or vast majority of it would get absorbed. It would be very power inefficient. Some of the characteristics of the waves themselves include the frequency, the power, the polarization. All of these will affect reception quality and the use of various components. And then there are a number of strategies for using the airwaves. We talked about a few different multiple access strategies by frequency, by time, by code, by space, and then a few other things like frequency hopping. The next lessons, we'll talk about the modulation process, the use of antenna, and then the use of the link equation to perform analysis.